morning. Well, thank you very much for giving me the opportunity to speak here today. This talk is really going to encompass some of the interactions that you might have between bacteria and iron minerals. And specifically, I'm going to be looking at magnetite. And the bacteria that I have focused on are iron metabolizing bacteria, of which there are many different types. So just to briefly summarize the outline of my talk, I'll begin with an introduction to the microbial iron redox cycle, because I'm not sure if all of you are familiar with this, followed by a brief introduction to what magnetite is. And then I'll go on to describe some of the results that I've collected over the last few years and some of the mineralogical techniques that I've used to try and investigate the magnetite and what's going on, followed by a brief discussion about the mechanisms that we think are ongoing, and finally the implications. And specifically, I just need you to remember the idea of we're thinking of magnetite as a biogeobattery, and that will come into the talk later on, but just keep that in your minds. Okay, so the microbial iron redox cycle. There is iron oxidizing bacteria and there is iron reducing bacteria, highly abundant in the environment. When we think of the iron oxidizing bacteria, there is three groups that we can consider. There's three groups that we really know of at the moment. These are nitrate reducing bacteria. These actually reduce nitrate, and this leads to the oxidation of iron 2 in the environment. And it's not quite sure whether this is an abiotically driven oxidation of iron yet, but still that's one group that we can consider. There is microaerophilic bacteria. These require a micromolar concentrations of oxygen and outcompete the abiotic oxidation, which then leads to the microbial oxidation of iron. And these sometimes form things like twisted stalks or sheaths, which you might have heard of. And finally, the one that I'm primarily most interested in is the phototrophic bacteria. These require light. So they actually, in the presence of light, they're able to oxidize the iron 2, leading to the precipitation of iron 3 minerals. And bear in mind, this is all pretty much happening at anoxic conditions in a neutral pH. On the other side of the cycle, we've got the iron-reducing bacteria. So these combine the oxidation of organics such as acetate or lactate, leading to the formation of iron 2. This can also be done with hydrogen as well. And these encompass bacteria such as Geobacter sulforeducens or Shewanella, which some of you may have already heard of before. When we consider the mineral phases that we work with, primarily when we're looking at iron oxidation, we might start off with the aqueous form of iron 2. So it's quite freely quite available in anoxic conditions, leading to the precipitation of minerals such as goethite, ferrihydrite, these iron oxyhydroxides. But there's also evidence that green rust and magnetite can also be formed through these processes. The iron reducers, they tend to start with more poorly crystalline mineral phases such as ferrihydrite. So it's got a high surface area, it's generally considered to be quite bioavailable. They can also use iron complexes such as iron citrate, and these lead to the formation of iron 2 minerals such as siderite. You can also get goethite formation if you have a very low concentration of iron 2 produced and reacts with ferrihydrite. But there's also the mixed valent magnetite, which is really the focus of my talk today. And bearing that in mind, the questions and the reason why I was thinking of this particular field of research is to try and understand whether there is in fact any minerals that can support both iron oxidation and iron reduction, basically whether it can act simultaneously as an electron donor or an electron acceptor. And for this, I focused on two different strains, the phototrophic bacteria Rhodopseudomonas pilastris Taiwan and the iron-reducing bacteria Geobacter sulforeducens. And of course, the mineral that I'm considering is magnetite. Due to the fact that it is mixed valent, should in principle mean that it could be available as an electron donor or an electron acceptor. So magnetite itself, well, for those of you who are not so familiar with it, it's got a very nice structure. It contains iron in octahedral and tetrahedral coordination. So there is, and this is what gives rise to its magnetism actually, because iron atoms are very magnetic, and they're able to, and the different lattice sites actually couple with each other in anti-parallel magnetization directions. So you kind of think of like a north and a south pole if you prefer. And so these up arrows are representing the direction of magnetization. And within the octahedral site, there is, in fact, for every one iron atom that's in the tetrahedral site, there is 2 iron atoms in the octahedral site. So you can think of the different magnetization direction arrows as you've got 2 going down and 1 going up. And effectively, the one down arrow and one up arrow cancel each other out. And so the magnetization really can be thought of as due to the iron 2, or more realistically, it's the iron 2, iron 3 ratio. And just to put this in perspective, when we have stoichiometric magnetite, we expect a certain magnetization value of around about 92 ammeters squared per kilogram. You don't have to worry so much about those units. But with maghemite, which is is the more oxidized version of magnetite, you see this value drops by around about 20% to 75. So this gives you an idea of the fact that you've got oxidized sample, it's less magnetic than the stoichiometric magnetite. Okay, so on to the experiment. Well, simply what I wanted to do was to try and see whether the presence of both of these different bacteria, these iron oxidizers or these iron reducers, might induce changes in the magnetite depending on various conditions. So for this, I just have a simple bottle. It's around about 50 milliliter volume. And then into this, I added 25 milliliters of media that can support both different bacteria. I then added about 10 milligrams worth of magnetite. The magnetite itself is very small. This is super paramagnetic. It's 12 nanometers. And you can see here from this image that the size is relatively uniform, actually, but it's around about 12 nanometers. So into this culture, I had the iron oxidizing bacteria, this Rhodopseudomonas palastris Taiwan, and also the iron reducers, Geobacter sulfur-reducens. When I expose it to the light, this basically stimulates the iron oxidizing bacteria. So these get to work. When I take it out of the light, put it in the dark, and incubate it in the presence of acetate, this stimulates the iron reducing bacteria. And of course, I can cycle between these 2 different processes, as I'll show you later on. And I quite like putting this slide on because this is just the instrument that I use. It's magnetic susceptibility, so it's a measure of how magnetic a sample is or how magnetizable a sample is. It basically applies a very weak magnetic field. But the reason I like putting this slide on is because the bottle itself, the culture, fits very nicely into the actual sampling tube. And no sample actually needs to be removed at any point during the measurement. So you've got quite an isolated system, and I think this is quite useful in comparison to many other different techniques where you'd require a small amount of sample to be extracted. And we can measure the changing magnetic susceptibility over time, and it's exactly what I have done. And you can clearly see here. So this, along the y-axis, is the relative change in magnetic susceptibility compared to the starting value. And you see very nicely that when we've added bacteria, so when we've added the iron-reducing bacteria in the light, this is stimulating the oxidation, you see this very nice decrease in the susceptibility. This roughly corresponds to a decrease of around about 8%. When we stimulate the iron-reducing bacteria, however, we see a very dramatic reversal. In fact, it's very quick. So it seems to be almost instantaneous, just a few hours. Why it's so fast, I'm not quite clear on that just yet. But clearly, we're seeing a reversal in this magnetic susceptibility. So something is going on. The bacteria, the oxidizing bacteria are what we think, oxidizing the magnetite, followed by the reducing bacteria are re-reducing the magnetite. And in fact, they actually seem to show a higher susceptibility than the starting material, which is also a little bit unclear right now. But to try and get an idea as to the mineralogy and to make sure that it's not just because we're not getting these changes just because the organics or the bacteria are sticking the magnetite together, I wanted to look at more of the mineralogy side of things. So I took a sample, the starting material, comparing it to the oxidized material, and finally the reduced material. And this will be the focus of the next few slides, just having a look at the mineralogy at these different time points. So when we look at it with X-ray diffraction, you see no noticeable differences between any of the samples. Okay, so that's maybe not so interesting, but it's showing that there's no extra mineral phases that are being produced by this mechanism. When we calculate the average crystallite size with Scher equation, we see no significant differences. They remain around about 11 to 12 nanometers. When we look at the lattice parameters, however, so we look at this position of the 311 reflection, we actually do see a very minor decrease. And this is actually quite important because there's an expression that has been published by Carolyn Pierce a few years ago. This expression here, she's called the master curve. And when we put the lattice parameter in this alpha, we actually can get an estimate or a calculation of the iron to iron 3 ratio. And so when we do this for our values, we actually see that the starting material has a value of around 0.47. And this is a comparison to a stoichiometric magnetite, which should be 0.5. So perhaps it's a little bit oxidized to begin with. But when we oxidize the sample, we see this decrease. So it goes to 0.42. And then when we re-reduce the sample, we get to a value of 0.47. So it's kind of indicating along the lines of what we're thinking, that the bacteria are oxidizing, the oxidizing bacteria are oxidizing magnetite, and then the reducers are reducing it. So for more evidence, we've also turned to Moss biospectroscopy. I'm not sure how many of you know of this technique, so I'm not going to go into too much detail, but essentially what happens is if you have something magnetic, you will get 6 lines. Okay? But here we've got this kind of shoulder feature here, and that's actually due to the fact that you've got 2 sets of 6 lines that overlap with each other. It's actually because we've got overlapping sextets from the octahedral lattice corresponding to this site in green, and the tetrahedral corresponding to this site in blue. So this is just an idea of what it should look like at room temperature. And of course, when we look at our samples, we do see this. We see this nice splitting. We see the tetrahedral sites. We see the octahedral sites. But what's interesting is that we don't see any significant differences between any of the samples. However, when we cool down the spectra, when we cool down the Moss and we look at these at 140 Kelvin, we actually start to see some differences. Primarily at this peak position here, you can see that this is non-splitted, whereas this has got some splitting for the oxidized sample, and in the reduced sample there is some splitting, but it looks clearly different from the oxidized sample. So something is different at 140 Kelvin, which is interesting because at 77 Kelvin they will look identical again. So something's happening, or we're observing some effect at 140 Kelvin, which we're not observing at these other different temperatures, the room temperature or 77 Kelvin. And for those of you who are familiar with the Verwey transition, at the moment I'm thinking this is probably what's happening, is as we're approaching the Verwey transition, there is some change in the electron hopping capabilities of the magnetite, and it's been induced by the oxidation of the sample or the reduction of it. But luckily for us, we can take the 140 Kelvin and we can apply an equation here, and we look at the relative area underneath the curves of the different sextets, and we can determine the stoichiometry. And so again, if we look at the stoichiometry, we see this value, the starting material is around 0.46, dropping to 0.42, and then going back up again to 0.46 when we've reduced it. So this is quite similar, in fact, to the X-ray diffraction that we calculated. But also it's similar, it shows, well, at least it shows the same trends as ferrozene techniques, which is a chemical assay. And we do see this starting value of around about 0.45. The error bars are a little bit big here, unfortunately, but it does decrease to 0.41 and then follows by an increase to 0.452. So we've shown 3 independent techniques that are seeing this same trend, this oxidation followed by the reduction of the magnetite. And that's quite useful because primarily we consider magnetite as being quite a crystalline mineral phase that isn't really very bioavailable. So we're seeing the trends that we're expecting, and we think these differences that are observed at 140 Kelvin are due to this Verwey transition. Okay, and the final kind of more mineralogical based technique that I'm showing here is temperature dependent susceptibility. So magnetite itself is, if you heat it up, it loses its magnetic capabilities, and this occurs at the Curie temperature. So basically it's non-magnetic above a certain temperature. So we heat our sample up and then we cool it. And so for the first sample, for the T0, for our starting material, we see no significant differences between the cooling curve and the heating curve. This is indicating that our starting material is quite stable, it's roughly stoichiometric, which we already know. However, when we've oxidized our sample, you can clearly see a shift. This cooling curve has actually shifted, the peak has certainly shifted into the positive direction along the x-axis. And this is indicative of maghemite-like characteristics. And if you remember, the maghemite is the oxidized version of magnetite. And what happens is at higher temperatures, maghemite gets transformed to hematite, so it loses its contribution to the magnetization. So what this is the fact that we've still got this increase in susceptibility, though, does indicate that our sample still retains some magnetite. So this is leading to the idea that we've got sort of a core shell model. So we think the outside of our magnetite is becoming maghematized, and then the core remains as magnetite. Interestingly, though, the reduced sample looks a little bit more similar to the oxidized sample than the starting material, which is what we kind of hoped it would look like. There are some small differences that exist, but this is leading us to think that perhaps this outer layer, the reduction process, isn't quite so complete. The fact that the bacteria are able to reduce the outside, this maghematized layer, but in fact it's not quite coupled to the core. There's like some sort of, almost like an onion skin worth of magnetite. But this idea is still a little bit up in the air, and really I think we need to be looking at microscopy to really get to the bottom of this. So just to sum up the mechanism that we think is going on here, we have our iron oxidizing bacteria, and they are taking the electrons out of the magnetite. They are maghematizing the surface layer. They're using it in conditions that suit them, and they're oxidizing the magnetite. The iron reducers are pumping electrons back into it. So they need to basically send their electrons back into the magnetite and get rid of them once they've oxidized the organics. And so at the moment we don't think that this surface layer is quite coupled to the core, but we're still not so clear about that right now. One reason this is quite useful or quite important is because iron metabolizing bacteria, in order to oxidize or reduce the magnetite, there needs to be some direct contact between the mineral itself and the bacteria, because we don't have any electron donors that have been added in here. And this has been known for Geobacter for some time, that cytochromes present in the cell wall in fact permit the transfer of electrons across the periplasm, and this can then in turn reduce the iron 3. With Taiwan, it was a little bit unclear, although a recent paper that came out just this year has demonstrated that the Taiwan is able to oxidize solid electrodes. So that would support the idea that we could oxidize solid surface such as magnetite. And so that's very useful, and they have some sort of cytochromes or analogs to cytochromes that permit this. And now just to quickly go back again to this idea of cycling. So I mentioned before that we could put it in the light and we could put it back in the dark, and then we put it back in the light again. And what you can clearly see is that once we've oxidized our sample to begin with, we see a decrease in susceptibility. Then we reduce it, so we stimulate the Geobacter, and we see this increase. I think this battery is going. When we put it back in the light, however, we see this decrease in the susceptibility again, and then we re-stimulate the Geobacter, we add a bit more acetate, we put it back in the dark, and we see this reversal of the susceptibility again. So sort of demonstrating this process could be cyclic between light and dark conditions, or more like day and night conditions. And this is where we're coming up with this idea of a biogeobattery, the idea that magnetite could support different types of iron metabolizing bacteria depending on the conditions that are present. So for instance, you might have conditions where water levels are low and you've got oxygen penetration or light or nitrate concentrations that are sufficient for the iron oxidizing bacteria. So in this case, the bacteria are taking the electrons out of the magnetite. They're basically discharging this biogeobattery. Later on, you might have in the dark, or the water level might have risen, and you don't have the same penetration of the oxygen, the light, or the nitrate. And at this point, the Geobacter are now pumping their electrons back into the magnetite and recharging the battery, ready for the next process when the oxidizers might be requiring it. And so this is the idea that we've got behind this biogeobattery, and it extends to various different environments, because around the world there is a large abundance of magnetite, whether it's in lakes and sediments, in these Chinese loess plateaus, or in iron sands found in New Zealand and California. I mean, these are just some examples. And I decided to add this slide and the next slide based on what we saw the other day on Tuesday with these magnetotactic bacteria, because these are existing in many different environments, but they contain the magnetite within their cell, actually. And we talk about them following the Earth's magnetic field. And as I say, I just added this slide because I thought it'd be interesting to consider the idea that although the magnetotactic bacteria, we think of them as the magnetite helping them to follow the Earth's magnetic field, well, perhaps they also have a dual function. What if the magnetite crystals themselves are actually able to support electron storage. Perhaps they could be used as batteries themselves, but of course this is just a very brief idea that maybe we want to consider at some point in the future. But to go back to my work, we've got iron-reducing and iron-oxidizing bacteria, these iron metabolizers. They're able to induce changes in the stoichiometry of magnetite. They can change the magnetization. And this, at the moment, we think this is constrained to the surface. Of course, the way of testing this would be to use larger crystals. And I have done some experiments with this, and we've got tentative evidence that supports the idea that it's a surface-constrained effect. And finally, we've believed that this can be cycled from one phase to another, oxidation or reduction, and they're supporting the idea of magnetite being used as a biogeobattery. But with that, I'd just like to thank you for your attention and acknowledge the people who have been involved with this work.